Welcome back, students. In the previous videos, we were talking about what happens when you apply an AC voltage to different circuits, the pure resistor circuit and then the pure inductor circuit and also the capacitor circuit. We derived expressions for them. And we said that in the case of a resistor circuit, the current and the voltage will flow in the circuit hand in hand, meaning that if the voltage is 0, the current will be 0, and if the voltage is maximum, the current will be maximum, and if the voltage is minimum, the current will also be minimum. So they're going hand in hand at the same time. In the case of an inductor circuit, we said that the current will lag the voltage by 90 degrees in the sense that if the voltage reaches 0 first, the current will reach 0 a little later. The voltage reaches maximum first and then the current will reach maximum a little later. So we said that the current lagged the voltage in the case of an inductor circuit. And in the case of a capacitor circuit, we said the current leads the voltage in the sense that the current reaches 0 first and then the voltage reaches 0. The current reaches maximum first and then the voltage reaches maximum next. So we said that the current in a capacitor circuit leads the voltage. So the current lags the voltage in an inductor circuit and the current leads the voltage in the capacitor circuit. We saw that. You have to be careful which voltage we are talking about. Are we talking about the voltage across the capacitor or an inductor, or the applied voltage? Let me draw the pictures first and let's see. I take a resistor circuit, so I have this AC applied across this resistor. I'll call this VR and I call this V. So there is a current I that flows through this. So this V is equal to Vm sine omega t. And this I is going to be equal to Im sine omega t because they're going to be hand in hand. So this voltage will be equal to this VR, right? This is R and IR will be equal to V. So in the case of an inductor circuit, so this is V, saying Vm sine omega t, and there is a current I that flows through this, and there is this L, and there is this VL. Okay. So here in this case, VR is equal to V because that's the only place where the voltage gets dropped, and here also this VL is equal to V. And VL is also equal to L di by dt. That's different, but you can see this. And the third circuit was this capacitor circuit. I had a capacitor here, that is C. The same V is going to Vm sine omega t is applied, and I is here, and then this is called as Vc. Then here also Vc must be equal to V. Okay. What happened to the current here? The current was lagging the voltage, meaning that I was equal to Im sine omega t minus pi by and here the current was leading the voltage, so this was equal to Im sine omega t plus pi by 2. I want you to focus on this. I want you to pay attention to this. So there is no voltage drop in this circuit than across this capacitor. Then again, there is no other voltage drop than across this inductor. And there is no other voltage drop than across this resistor. So VR must be equal to V, VL must be equal to V, and VC must be equal to V. So the current was, when I say the current is lagging the voltage, or lagging the voltage here, then it is lagging both the voltages VL and VL. When I say the current is leading the voltage, then it is leading both the voltages VC and V. Suppose I take another circuit. Let's suppose I combine these. Like suppose a practical circuit where I have a resistor and also an inductor. Okay? So clearly you have V is equal to Vm sine omega t. So this is the voltage you apply. This is your reference voltage. Okay? So this is the voltage you apply. And then I have an R here and I also have an L here. So clearly there is a current that is going to go through this. And now you see there would be a VR across this and there would also be a VL across this. So now notice that VR plus VL will be equal to V. Right? Okay. So what did we say first? The current, if in the resistive circuit the current is hand in hand with the voltage, and in the inductor circuit the current is going to lag the voltage. But if the voltage is V, the current cannot do that, cannot do both at the same time. How can current be hand in hand with this voltage and also lag this voltage at the same time? We have a single current, right? And a single voltage. So when we say that the current is hand in hand with the voltage, this current is hand in hand with this voltage. And this current will lag this voltage. Okay? This one. And it will have some relation with this voltage. I want you to understand this. In this circuit, it is okay to assume that the current is hand in hand with this voltage and this voltage, because there is no other voltage drop. And it's perfect to assume that this current will lag this voltage and this voltage, because there is no other voltage drop here. And it is okay to understand that this current will lead this voltage and this voltage, because there is no other voltage. But here that is not the case. You see here, this V must be equal to VR plus VL at any and every point in time. So the combination of these two voltages must be equal to this voltage. And there is only one current, and there is only one this voltage. But we say that the current goes hand in hand with the voltage. Which voltage? This voltage. And the same current will lag this voltage, the voltage across the inductor. And if there is a capacitor, then the current will lead the voltage across the capacitor. Okay, and you will have some relation with this voltage. I want you to understand this. This is very critical. Okay, so With this in mind, we will go on to discuss what is called as the Phasor diagram. You know that a sine function can be related to circular motion. Okay? For example, let me take this function y is equal to a sine omega t. Some function y of t is equal to a sine omega t. If you remember, this can be written or this can be represented like this. I can take a rod A or something, a rod of length A. Let's say this is the center, and let's say we take a rod of length A. Okay, this is length A. And if I rotate this rod in this direction, anti-clockwise direction, so I start from here. Suppose I start from here. It is 0, right? So like time is 0. The rod is 0. Then I start rotating it. At time is equal to t, I get to this position, and this is actually theta, right? And that is also equal to omega into t, because I am rotating it with an angular speed of omega. So this theta, okay, is equal to omega t. So this is a rod. If I rotate this rod around this, so you see the projection of that along the y-axis is going to be equal to y is equal to a sine omega t. At time is equal to 0, the projection of this rod on the y-axis is 0. There is nothing there. So the shadow of that on the y-axis, that is what we mean by the projection of this on the y-axis, the shadow of this. So at time is equal to 0, there is no shadow, it's 0. Y must be 0. But time is equal to t, then you would have covered an angle theta, omega t. So the projection of that, this length, is equal to a sine theta, which is a sine omega t. So that's the length of the shadow on the y-axis. Right? So the value of y at any time t is given by this expression, y is equal to a sine omega t, and that is actually the rotation that you effect here, right? So the projection of, suppose it is in this position, the projection of that on the y-axis is a value. The projection of this rotation on the y-axis is this. We have come across that already. Okay? If you want this y value, then that y value is equal to a sine omega t at time t. So if I am at some other position, going in a circle, right? So suppose if I am here after some time, then what is the y value then? So that this is y1 and this is y2, and that would be, this is theta 1, and now I would have gone theta 2, and this will be in omega t2. So this value y2 will be this length, right? That projection on the y-axis. So that would be, if y1 is equal to a sine omega t1, then y2 will be a sine omega t2. So a sine function can be treated as the projection of a rotational motion on the y-axis. Okay. Once we get this, then we will go on to do what is called as the Phasor diagram. In an alternating circuit, what is the voltage? V is equal to Vm sine omega t. So I can represent this as a phasor, like we did for the y function just a little while ago. So it's like this. I'm going to have this one. So this length is Vm. So this is Vm. The length is Vm. The length of this vector is Vm. Okay? And I start from here. This is a time t. And I'm going to rotate that vector in the anticlockwise direction about this axis. And this is my origin. So if I do that, then V at any point, suppose this is omega t, this is theta, right? This is theta is equal to omega t. So the projection of this vector along the y-axis at any point in time t is your V. So V here is equal to Vm sine omega t. So that's the value of V. So this is what you call as a phasor. Okay, a phasor is a rotating vector. Rotating vector. And what is the length of that vector? The length of that vector, the magnitude of that vector, is equal to the amplitude of this function, which is the maximum value. So as it comes here at 90 degrees, then you are going to have the longest projection on the y-axis. In that case, this V will be equal to Vm. So, and when it is here, at time is equal to 0, the projection on that is on the y-axis is 0. So the magnitude of this vector is Vm. And this is not a vector at one place. This is actually a rotating vector. So this keeps rotating like that. So you call this as a phasor. Now I've represented voltage as a phasor. And at what time am I going to mention it here? You know, should I mention it at times equal to 0? Should I draw this, when I draw this, should I draw it when time is equal to t by 2 or t by 4? Or at 3t by 2 or any other t? What time would I choose to draw this phasor? I can choose any time. I could even choose time is equal to 0. If I have chosen time is equal to 0, then my graph would be something like this. Okay, so this is actually my Vm. Okay, and I'll say that this is rotating like this. And now time is equal to, this is my omega, right? Omega. The time is equal to 0 here. So this is my Vm. And if my time is equal to t, then it will be here. So this is the same phasor at time is equal to 0. And this is again the same phasor at some time t, a non-zero t. These are equivalent. Which diagram should I use to write this expression? Well, I can use either this diagram or this diagram. They're equivalent. Why are they equivalent? Because I have drawn this diagram at some time t. Here I have drawn the same diagram and time is equal to 0. They are equivalent. I can either draw this, I can either or this. It doesn't matter. They both represent the same thing. I have given omega, I have given Vm, and I say that this is Vm, the phasor is here at time is equal to 0. So clearly at times equal to t, it's going to be here. Same thing. So there is no difference. Okay? So a phasor is a rotating vector. And this is a phasor diagram. I've drawn it for just the voltage. But you use a phasor diagram to draw both the current and the voltage in a circuit. And the different parts of the circuit. Okay, you draw both the voltage and then the current. The phasor diagram gives you the relationship between the voltage and the current. And how would I draw the current? Again, the same thing. I'm going to take the maximum value of the current I. Why? Because I is equal to Im sine omega t if it's a resistor, right? Both will be in phase. That's what we call as in phase. They move in tandem, which means if the voltage reaches maximum in the circuit, the current reaches a maximum at the same time as the voltage. The voltage becomes 0, the current is also 0. The voltage is negative, then the current is also negative. They move in tandem. So only then you will have Vm sin omega t and I is equal to Im sin omega t. So this happens in the case of a resistive circuit. So what would I do now? I would have, I'll probably use a different color now. For current, I can probably use this, right? So this will be like that, Im. And that is also moving, omega, right? Okay. So both of them are along the same line. At t is equal to 0, I is also equal to 0. I value is again the projection of Im on the y-axis. V value is the projection of Vm on the y-axis. So I can either draw it like this, or equivalently I can draw it like this. This is my Im. Same, right? When Vm is here, Im will also make the same angle in the sense that the projection, it will get this value, and Vm, the voltage will have this value and the current will have this value at the time t. And when Vm comes here, then you will have V will be Vm. Im will also come here at that time. So I will be that time. So both to represent these two quantities, V is equal to Vm sin omega t and I is equal to Im sin omega t, I can either use this picture or this picture. Okay, this diagram or this diagram. They both are equivalent. Just that I have drawn this diagram at time is equal to 0 and I have drawn this diagram at time is equal to t sometime. I say when Vm is here, this is how things look like. So a phasor diagram gives you the relationship between the current and the voltage in a circuit. Instead of doing it mathematically, I can visualize it, I can see it as a picture. By looking at the picture, you know what's the value of V? Yeah, projection of this. This is the value of V. What's the value of I? Projection of this. This is the value of I at that time. You come here, at time is equal to 0, what's the value of V? Projection of this, 0. What's the value of I? Projection of I on the y-axis, 0. So you can clearly see this, pictorially. Rather than looking at it in the mathematical form, you are looking at it as a picture. So the phasor diagram helps you get the same information pictorially. Okay? So let's start doing the phasor diagram for different circuits that we've discussed. Okay, first for the resistive circuit. R. Okay? So I am going to have this. And I can do it at any time. I can do it at t is equal to 0, or you can choose random t, and I can draw the picture. Okay, I'll just choose a random t now. Okay. Say at some time t, let us suppose my v is like this. This is my Vm, right? Vm. So this is omega t. Okay, and the vector is rotating in the anti-clockwise direction. So at that time, then this is my v value, projection of this vector along the y-axis. So this is the v value at. So my v is equal to Vm sine omega t. And what's my I? I will be in tandem, right? So it will move hand in hand with Vm. So this is my I. And this is my I. My Im maximum, right? That's the magnitude of that. So this will be I at that time. I at that time omega t. So I is equal to Im sine omega t. So this is a phasor diagram for a resistive circuit. The resistive circuit. Okay. And what would be the phasor diagram for an inductive circuit? Okay. Same. I'll have this plane of rotation. So again, I can choose it at any time. I'll choose some random time t. At some random time t, I say my v is equal to Vm sine omega t, right? So I'll choose. I can choose my v vector at any time. I'll just choose this at some time t randomly. Okay. So this is my Vm again. So this is my omega t theta, and the vector is rotating like this. Here. So this would be my v. So projection of this Vm along the y-axis is v. This is the value of v at time t, some random time t. Okay. If I had got it here, I could have even drawn it like this, right? I could have done that. It's equivalent. Okay, so what's the current in an inductive circuit, in a pure inductive circuit? So I is equal to Im sine omega t minus pi by 2. So what does it mean? It means that it is lagging the voltage. So what it means is that the voltage reaches the peak first and then the current reaches its peak. Okay, so this current now is not hand in hand with this, but then it is going to lag this by 90 degrees. So the rotational direction is this. So the voltage must come first and the current will come next. And then the difference between them is 90 degrees. Or I should use a different color. Okay, so this is my I. So the angle is between them is 90. So this goes and like it comes later. So they move together like that. Okay, so they are like this, 90 degrees to each other. Okay, if this is a blue is a voltage, and if red is a current, then they rotate like this. So first it reaches maximum, and then it reaches the maximum, and then like that. So they rotate together now. Okay? They both have the same omega speed because it's like they're tied together. Okay? They move with the same omega angular speed, and one follows the other. This is the voltage and this is the current, and the voltage follows the current follows the voltage in the same direction. So that is what we got here. Okay. So at time is equal to 0. So yeah, this is one way of drawing it. Another way of drawing it would be the same. I could have, it is equivalent. I could have drawn it like this. I could have also drawn it like this. Like this. I do this in blue. Okay? I do it. Equivalent. Okay? This equivalent. I could have drawn it like this also. So this is my plane of rotation. I could have taken Vm like this. If I had chosen Vm like that, then my Im should be here. Okay, this is my Im. Again, so the angle between them is 90 degrees, and it's going to rotate with an omega. So whole thing will rotate. So they are equivalent. I could have drawn it like this also. So both are the same. Here I have taken the time to be 0. I have taken the snapshot when time is equal to 0. Here I have taken the snapshot when I have some random time. But both are equivalent. I could have drawn like this also. I want you to keep it in mind. This is also okay. And third, capacitive circuit. Capacitive circuit. Again, I will have the plane of rotation. And then I take some random time. At the random time, the voltage is 0. The voltage phasor is 0. Okay? So this is angle is omega t, and then this is Vm. And something like that. But what about the current? The current must be leading the voltage, right? So it cannot follow this. It should have gone ahead of that. So the current would be somewhere here. So at times it's equal to T, then the current would be here and the voltage would be here. So this will give me, okay, I will do this. Here it is B. This is my I at that time, and here this is my I, and this will be my V. So this is the value of V and this is the value of I. So mathematically, you see, so Vm, so V is equal to Vm sine omega t, and I is equal to Im sine omega t plus pi by 2. So this angle is 90 degrees. So this is a phasor diagram for a capacitive circuit. This is the phasor diagram for the inductive circuit, and this is the phasor diagram for the resistive circuit. Okay? So the most important thing is, what is this voltage? Is this applied voltage? No. This is the voltage across the resistor. And what is this voltage? This is also the voltage across the inductor. And what is this voltage? This is the voltage across the capacitor. Okay? And because the in a pure circuits like this, the applied voltage is equal to the voltage across the inductor or capacitor, we consider both of them equal. But this phasor relationship is between the current in the inductor and then the voltage across the inductor, the current in the capacitor and the voltage across the capacitor, and the current in the resistor and the voltage across the resistor. That is this relationship. Okay? Now, why do you need this phasor diagram? Phasor diagram helps you analyze electrical circuits very easily. We'll see that now. So far, we did the phasor diagrams for individual things like resistor, capacitor and inductor. I'm going to combine them all now. I'm going to have one circuit where I have a resistor, capacitor and inductor, and then see how this can be analyzed. And as a first step, we will draw the phasor diagram for that circuit. Okay? This is my circuit. This is my AC power supply, and then I have a resistor and an inductor and also a capacitor. I connected them all together. Okay, so this is V, the applied voltage, right? And this is, I have R here, and then L here, and then C here. So a current I will flow through this circuit, resulting in a voltage drop across this resistor R. This can be given as VR. Okay, and then a voltage drop across this inductor can be given as VL, and then the voltage drop across this capacitor is given as VC. See, mathematically, I can write an equation for this. So, what is my VR? My VR is equal to IR at that time. At any particular point in time, the current that flows through the circuit multiplied by R will give me the voltage drop across VR. And what is my VL? My VL will give me L di by dt. So what is my VC? VC is equal Q by C. This I know. So let me take just some point in time. Okay. So at that time, at that instant in time, see, this is positive, this is negative. The current is flowing in this direction then. So this will be positive, this will be negative, and this will be positive, this will be negative, this will be positive, this will be negative. At that instant. So if I do the Kirchhoff's law, the voltage law for this, then I will start from here and then I will come back to the same point. So that will give me this equation. What is the equation? This will be IR. This is positive, I am entering positive, so this is also positive. Then I am entering here positive, and that is also L di by dt. Then that would be again entering positive, so Q, C. Then I am entering negative, so minus V equals 0. So I will have this, right? I will have IR plus L di by dt plus Q by C is equal to V. So this is what is called as a differential equation. Okay, I mean I can take it further. I can represent the whole thing in terms of Q. Why? Because what is I? I is dq by dt, right? And what is di by dt? Then that will be d squared q by dt squared. So I know that I is equal to dq by dt, which means di by dt is equal to d by dt of dq by dt. So this is written as d squared q. So this, if I put this in here, then I'll get r into dq by dt plus L into d squared q by dt squared plus q by c is equal to v. And if I rearrange this, I'll bring this first. L d squared q by dt squared plus r dq by dt plus q by c is equal to v. Okay. So this is v sin omega t over omega. Okay. So this is Vm sin omega t. And let me stop with that. This is going to be a function of time clearly. So that's also a function of time. So this is called as a differential equation. This equation has a solution, and you will study about it when you do differential equations in your mathematics subject. I'm not going to address it now, because if you want to find the solution mathematically for this equation, then it's going to be a little complicated, and you should know how to get there. So I want you to learn differential equations first in your mathematics before we even do before we even find the solution for this, before we even do this mathematically. But it's a little complicated there. But I'm going to find the solution for this. I'm going to find the resultant using the Phasor diagram, which is much more easier to do for us. We will do the Phasor diagram for this now. So what do I know? I know the relationship between the current that is flowing in this circuit and the voltages across the resistance and the inductor and also the capacitor. I know that. So using this, I should be able to find the relationship between the current and this voltage, the applied voltage. So that's what we'll do. I'll have the plane. Okay. I'm going to take the currents as a reference vector. Okay, current is what it takes, the reference. It's the same. Like so, when I say that the current lags the voltage, it means that the voltage leads the current, right? And when I say the current leads the voltage, which means that the voltage lags the current. So it doesn't matter at what time you are looking at it. At any point in time you look at the picture, this is what should be happening. So I'm going to look at the picture when the current is zero, not when the voltage is zero, not when time t is equal to 0. I'm going to look at the picture when the current is 0. Okay, so that's the time. at that time, how will other quantities will relate to this current? That's what we'll see now. So I'm taking a time instant at which the current through this circuit is 0. So that would be here, right? I must be 0. This is the time. There is some time at which the current is 0, and this is it. This is a picture. Okay? So the projection of this along the y-axis is 0, so the current is 0. So current phasor will be like this. Okay? So everything will go with an angular speed of w, omega. Okay. So when current is like this, what would be VR? VR, the voltage across the resistor, will always be hand in hand with the current. So VR at any point at that point in time, it should also be 0. It should be here, right? So the projection of that should be 0. So the current would also, the voltage VR would also be like this. So this is where the current is, the current phasor is, and VR phasor will also be along the same line, in the same direction. Okay, VR. But what about VL? Current is like this, inductor. So VL must lead the current. Why? Because the current lags the voltage in inductor. So the voltage must lead the current. If the current is like this, then voltage must be, VL must be 90 degrees to the current. So VL must be here. So VL is here, but at that time I'm seeing VL is here, so the current must lag this by 90 degrees, so the current is here. It makes sense. And what about VC? The voltage across a capacitor. The voltage across a capacitor must lag the current. Why? We said that the current in a capacitor leads the voltage. So if it is here, then if this is the rotational direction, then VC must be 90 degrees behind it. I'll probably do this. So this is VC. Maybe I should use a different color. I better use it. This is my VC. So VR is this, VL is this, and VC is this. I hope you understand this. Then what is V at that time? Where would the V vector be? Well, what do we know? We know that V is equal to VR plus VL plus VC. Right? So vector, if we take this to be vector, it's like VR, V is equal to VR plus VL plus VC as a vector addition. Okay, so here I consider VL to be greater, VC to be smaller, so the net of these two vectors will be here. Okay, and this is VL plus VC. This is going to be VL plus VC. This is the vector I get. And this has to be added with VR. VR is here, so this must be your Vm. So because V is equal to Vm sin omega t, so Vm is this. So I get an angle theta, or as consider this phi. some angle. So when Vm is here, Im will be here. You notice this is not 90 degrees, notice. Im is 90 degrees to Vm. Im is also 90 degrees to Vc. But Im is not 90 degrees to V. Now it has some angle. Okay? I want you to understand that. So Im is not leading or lagging and in hand in hand with this at the same time. That doesn't happen. I told you I is hand in hand with Vr. I lags Vn. I leads Vc. Then I, now you can see from the rotational direction, I lags Vm by this angle phi. That is not 90 degrees, notice. Because I've added these vectors, I got phi here. So Im lags this Vm by an angle of phi. So I can say that V is equal to Vm sine omega t. So from this diagram, V is equal to Vm sine omega, V is equal to Vm sine omega t. You notice that the current is lagging this voltage by an angle phi, right? So that would be I is equal to Im sine omega t minus phi. So this is what is happening here. So this is lagging the voltage by an angle phi. What would happen if Vc was greater than Vl? I mean, that is not an unimaginable scenario, because if L or C changes in the circuit, then it is quite possible that you have a lower VL and then higher Vc. In that case, the resultant of these two vectors would be in the negative y direction. And if you add that with this, then your V would be here. Had Vc been greater than Vl, then this would be here. So in that case, I will be leading the voltage. Okay. So this equation will be slightly different. Then I will be equal to Im sine omega t plus phi. I will be leading the voltage. You see, that brings us to one conclusion. When you have a circuit that has all these elements, resistance, inductance and also capacitance, it is possible for the current to either lag the voltage, the applied voltage, or lead the applied voltage. The current will always lag the inductor, and this voltage VL. The current will always lead Vc, but it is possible for it to either lead or lag the applied voltage depending on the value of L and C in the circuit. So if it is going to lag the voltage, lag the applied voltage, I can say that the inductive effect is more than the capacitive effect in the circuit. If the current leads the voltage, then I can say that the capacitive effect is more than the inductive effect. It doesn't have to be 90 degrees, obviously. It won't be 90 degrees because you're combining a lot of things here. You'll have some angle by which the current will either lead or lag the applied voltage. So, if the current lags the voltage like this, we say that this circuit is net inductive. If current lags voltage, the circuit is net inductive. Because only in the case of inductance the current will lag the voltage. In the pure inductance 90 degrees. But here it doesn't lag the voltage by 90 degrees but by some other angle. But still it lags. If it lags, then this effect is dominant. And if current leads the voltage, then this is net capacitive. The circuit is net capacitive. I want you to understand this.